Hello and welcome to another video. Today I'm going to talk to you about the Drude model, or also called the classical electron theory. It was firstly proposed by Drude, and it's one of the first theories we have that describe how free electrons, move into metals. So we have a few assumptions, and they are recalled from the kinetic theory of a gas. So we are assuming that all electrons behave as free particles. All of them contribute to both electrical and thermal properties, and we're going to define tau as the mean scattering time, and its probability of tau is dt, which is a small interval of time over tm. And all electrons are influenced by both electric field and magnetic fields. So we're going to look at the most important equations for electrons in an electric field just alone, which is the force is equal to minus the electric charge times the electric field E. And if we substitute it in from actually the equation of, I'm going to write it in green here, which is dp over dt is equal to the force minus p over d. Now, this equation is important because it's both used in the electrons in only electric field and the both electric field and magnetic field over here. So if we plug this equation into here, into the F, we'll see that we get to this equation. And we also get that the current density J is equal to current over area. This is a really important equation as well for a later example that we will see. And we also get J is equal to conductivity times the electric field, Ohm's law. And we get also this equation for conductivity, which represents the number of atoms per unit volume in the metal times electric charge squared times the scattering time tau over the mass of the electrons. So this is what happens in an electric field. Now we can include the magnetic field B as well into the equation, and again, if we plug this equation of the force into this other equation in green, we will see that we get dp of dt is equal to minus the electric charge times the electric field plus the velocity of the electron that are scattering in the metal cross the magnetic field minus p over the scattering time. Now, from these equations we get two very important equations as well, which we will need later, which is the electric field is equal to the resistivity times the current density, and the current density is equal to, again, conductivity times E, which is the same one as we had over here of Ohm's law. Okay, so the only thing that I haven't written down is that the resistivity and the conductivity have an inversely proportional relationship, so you can interchange them depending on what the question asks you. So we need to define one more thing which is important, which is the resistivity matrix, which is this thing over here. And once you write it down, you get all these terms, and the diagonal of the matrix is actually something called the Hall effect, which is written over here. So the Hall effect is really important, and it's defined as when a magnetic field is applied perpendicular to a current flow of a voltage, it can be measured perpendicular to both. So the Hall effect is important because it's used in the metals, and it's used in many many questions that we'll see an example later which uses the Hall effect as well. But basically it's when the magnetic field is applied perpendicular to a current flow. And it is defined by the resistivity matrix over the magnitude of the magnetic field, and also it's defined as -1 over NE. Now this is not always like this, but sometimes it can interchange signs, so we'll see why in the next video. So these are all the electronic properties. Now we're going to move into the thermal properties of the electrons in a metal, and we're going to define the conductivity, K. We have this definition of the heat capacity, CV, is equal to 3 over 2 kB. Now this comes from the kinetic theory of an ideal gas, and we'll see later that this is actually incorrect per the electron, and which is written down here, and it will soon be fixed by the next theory. Okay, so these are the different thermal properties, and we have these equations which are important, which is the velocity root mean squared, and again the conductivity K. Okay, so now I want to look at an example which was from one of my seminars, and I think it really helps to understand and put in practice this topic. So we have an isotropic metal with a valence of 2 and the scattering time of 2.61 times 10 to the minus 14 seconds, and it's a whole bar. So again, this whole coefficient this is what we're talking about in this example. So we have a bar. I haven't drawn it in 3D. I'm just gonna sketch it like this, and with length C, and width A and depth B. It tells you the dimensions, and then it also tells you that there is a current along the length. So along C, there's a current I, and there's an EMF applied of 0.8 across C, so this way. Calculate the number of atoms per unit volume. So again, number of atoms is N, let's remember this, in the metal. So where do we start? Well, we immediately jump to the conductivity equation, because that's where it has the scattering time in it, and that's something that we have. And so we write it down. This is our equation, and we need to find N. So when we see that we have the conductivity term, and then we have the scattering time and a bunch of other things. So immediately I jump to this equation, which again is the inversely proportional relationship of the conductivity, so it's 1 over resistivity. Now the resistivity we also know from these are the equations that we derived earlier, that is equal to the electric field is equal to resistivity times the current density. So we write it down, and then we also know that the current density is equal to the current over the area, or the cross-sectional area, which we also got here in the beginning. And we also know that the electric field is equal to the EMF over the length of the bar, which in our case is C. So then we write everything down and we substitute it in the equation. So sub in for the electric field, sub in for the current density. So you get the mass of an electron, and then you get the voltage, EMF, over the length, and then over the current divided by the area, cross-sectional area, times the electric charge, the charge of an electron, squared times the scattering time. Now, we need to make sure that we put everything in standard units, so SI units. So I use kilograms for mass on electrons, and then, volts for EMF. So when we have it here, EMF, remember to get everything in SI units, also this, and everything else as well. Now, we need to remember to divide by 2, because in the question it says that we have a valence of 2, so of 2 electrons. So we need to remember to divide by this factor of 2. And then we'll get the answer in meter minus cube. So we need to convert it into centimeters per centimeter cubes, because that's what the question was asking for. So now that we have successfully calculated the number of atoms per unit volume, I hope that you enjoyed this mini video, and I hope that you understood this content a little bit better. Okay, thank you for watching, and bye.